welcome back. This is an Aleks training video on using the molecular orbital model to predict bond order and paramagnetism. Something is magnetic if it has unpaired electrons inside, deep inside, that can't be described by the Lewis dot structures. Remember, the Lewis dot's just dealing with the valence electrons on the outside and making bonds. But if you were to have something a little more detailed and you could see where all the electrons were, you could describe something like magnetic. So we're going to see that if it is unpaired, okay, so paramagnetic is unpaired electrons. Diamagnetic, which is repelling, it repels a magnet. Diamagnetic is no unpaired electrons. Okay, so that's pretty simple. Stable and unstable has to do with the molecular orbital, the orbitals. So let me show you something. I pulled this up so I wouldn't have to draw the boxes. The only problem is I'm going to have to make one little modification. This box here, okay, for anything less than group 6 is actually higher than this one, okay? So this is going to be the sigma 2p, okay? All right, so when I fill, I'm going to fill this one first, second, and then these two, and then this one, okay? All right, the first one that they're asking us to do is boron. All right, so boron, according to the periodic table, has 5 electrons. Now this starts at 2s, so 1s1 and 1s2 is lower than this picture, so we'll just assume it's there. So that's 2 electrons, and then I need 3 more. So if I'm going to do 3 more, I'm going to do 2s1, 2s2, 2p1, and that's boron. Okay. Now let's do the same thing. 2s1, 2s2, 2p1. So we're going to fill this up. So we're going to start at the low and put, let's see, I've got 1, 2, 3, 4, or I've got 1, 2, 3, 4, 5, 6, 6 total. So I'm going to start here, 1, 2, now go to the ante 1, 3, 4, 5, 6. Remember, Hund's rule said you have to put a girl in their own room before you start pairing them up. Okay? All right, so if that's true, do I have unpaired electrons? I do, because in the, anything before group 6, this actually has higher energy. The sp2, or the sigma 2 pi, has higher energy than the pi 2p. So that means when I filled them in, I had to separate them, and now they're unpaired. So if they're unpaired, what's going to happen with boron? Okay, it's going to be paramagnetic. Okay, it's going to be paramagnetic since it's unpaired. Okay, let's do the stable and the bond order also. Okay, bond order just means you subtract all of the antibonding from all of the bonding. So you add up all of your bonding ones, all the ones that have electrons in the bonding orbitals, subtract the ones in the antibonding ones, and divide by 2 since you have one on each side. So we're going to have, I think it would be what? It would be n minus n star over 2, and that's called the bond order. All right, so I've got, in this case, 1, 2, 3, 4, okay? So I've got 1, 2, 3, 4, that's my regular bonding orbitals, minus 2, because that's in the antibonding. So 4 minus 2 is 2, divided by 2 is 1. So this is going to have a bond order of 1. So this is bond order of 1. And since it's more than 0, it's stable. So yes, it's stable. If you get a bond order that's negative or 0, it doesn't happen. You're not going to make a bond. But if you have a positive bond order, you will make a bond. All right. The next one is O2, but it's an ion, O2, 2+. Let's do this again. All right, so I'm going to have oxygen on both sides. And oxygen in the periodic table has 8 electrons. Okay, 2 of them would be in 1s1 and 1s2. Okay, so that means I'm going to have 6 more. So I'll have 1, 2, 3, 4, 5, 6. Okay, and I'll do the same on this side. 1, 2, 3, 4, 5, 6. All right, now that I have that, I'm going to just start filling in. So I've got 1, well, let's count how many I'm going to have. 1, 2, 3, 4, 5, 6. I'll have 12. 1, 2. Oh, I forgot. This is actually higher because it's up to group 6. Okay, this will actually go higher energy than the group pi 2p. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 12, 2, 4, 6, 8, 10, 12. Now that would be oxygen-oxygen. So oxygen-oxygen would be paramagnetic, but this was asking for 2+. Right? So 2+ is going to remove the last 2 electrons that we put on, and which means now I look and everything is paired. There's no unpaired. Right? So since it's unpaired, this is going to be diamagnetic. Okay, because it's 2+, took away those last 2. Now what's the bond order? Okay, I'm going to take everything that's not a starred and subtract the starred from it. So I have 2, 4, 6, 8. I have 8 minus 2 is 6. Okay, I remember the formula. It's n minus n star over 2. So I have 4 minus 2 is 6 divided by 2. It should have a bond order of 3, okay, which is positive. And so if I have a positive bond order, that means it's going to be stable. All right, so is it stable? Yes, it's stable. Is it diamagnetic or paramagnetic? Oh, I can't remember. It's diamagnetic. Okay, and what is its bond order? It was 6 divided by 2, it was 3. Okay. Now, what we're going to do with this third one is the same. It's oxygen, but instead of 2+, it's 1+. All right. So what's going to be this? How do I figure that out? It's going to be 1. I'll just leave this so you can see it. If I can do it, this will be 1. Okay, that means 1, 2, 3, 4. It's up here. 5, 6, 7, 8, 9, 10. Okay, and then it should have been 11, 12, right? But we're only doing a positive 1. So now I'm going to have 1 here. This is unpaired. This is going to be paramagnetic. Okay, paramagnetic. Now let's look at the bond order. I'm going to have 2, 4, 6, 8 minus 3. Okay, 8 minus 3 is 5. 5 divided by 2 is 5 over 2. So the bond order is, it's fractional, but it's still positive. Okay, so it's still going to be stable. Right? So it's stable. It was